Hello, my name is Michael Ashley and I'm going to be talking about Antarctic telescopes and the icing problems that can occur. So I've got a PowerPoint presentation which I'll just share, and off we go. So that background slide, very spectacular, taken by Geoffrey Chen at the South Pole in July 2020. Okay, so this is really a key graph. It shows the fraction of water vapor in the air at sea level as a function of temperature. So you can see there's a sort of roughly an exponential relationship. And at 20 degrees C, you have maybe 1.7% water vapor at 100% humidity. But as the temperature drops, the water vapor falls out of the air. And when you get down to Antarctic temperatures, down at -60 or below, there's hardly any left. In fact, when you get to -70, -80, the air is drier than a commercial cylinder of dry nitrogen. But it can still form ice on telescope optics, so we have to be concerned about it. Okay, so let's start by looking at the equilibrium between water molecules in the air and on a surface. So I'll draw a surface. In fact, I might just bear with me here. I'll just change a color. Okay, so this is a surface in a telescope. It may be reflective or it could be transmissive. And this is air outside the surface. Now, air consists of molecules, and let's draw a water molecule. It's oxygen and 2 hydrogens, and it's polar, which means that there is a separation between the charges, which makes water molecules stick to each other and also stick to surfaces. Of course, most of the air consists of nitrogen and oxygen molecules. I'll just draw a couple of those. Here's nitrogen, here's an oxygen. And these are all whizzing around at quite high speeds. And the typical speed is greater than the sound speed, and it's about 500 meters per second. So things are moving very quickly. Now, the size of these molecules, water molecules, about 0.3 of a nanometer in diameter, and oxygen and nitrogen are roughly the same. The separation between the molecules in Antarctica or at sea level, they're pretty much the same, is around about 4 nanometers. And the other interesting factor is the mean free path between collisions is of the order of 100 nanometers. Okay, so what's happening is that the water molecules occasionally hit the surface and they stick. And if enough water molecules build up, you'll start to get ice forming. Now, there's a natural equilibrium between the ice that's stuck to the surface and the ice that's in the air. And that depends on the temperature of the two surfaces. So let's call this T sub S for T surface. And this is T sub A for T air. And if they're at the same temperature, then the occasional water molecule will leave the surface and another water molecule will come down and stick to the surface, and you'll reach an equilibrium where there's essentially only a tiny amount of water on the surface. Where things go wrong is when the surface is below ambient air temperature. And that can happen due to radiative cooling, for example. And radiative cooling means that the surface can emit mid-infrared radiation, and at -60 degrees C, which is the typical Antarctic wintertime temperature on the plateau, this corresponds to a wavelength of around about 14 microns in the mid-infrared. So the surface sees the cold background of space and it cools down, heading towards 3 degrees Kelvin, but not getting there, obviously. And as soon as it's slightly below the temperature of the air, the problem is that the Antarctic air is pretty much 100% relative humidity, so it contains as much water vapor as it can. So any time that a surface is below the ambient temperature, it will start to accumulate water molecules. So what can you do about that? Well, you can heat the surface up, but And you only have to get it to ambient or just maybe a degree or so above, and the water will sublime. You can also try to prevent radiative cooling, and there are a number of ways of doing that. You can, if you choose an infrared transparent glass, which is transparent at 14 microns, then it won't emit 14 micron radiation, and so it won't cool by that mechanism. One issue you have to be careful about, though, is that as soon as the water molecules start to form a layer, water itself is a very good black body, so your transmission it'll become opaque very quickly, and you will start to cool down due to radiative processes. Okay, so preventing the cooling of the glass, you can do that with heaters. The other possibility, which I think is very interesting, is reducing the humidity of the air very close to the glass. Because this mean free path is only 0.1 of a millimeter. So if you can somehow take out the water molecules in a layer maybe only a millimeter or so thick, then you will change the equilibrium such that water molecules on the glass will go back into the air. So that's really all it takes. If we can make a layer just a millimeter thick of low humidity air close to our optics, we are 99% of the way to solving the icing problem. And where can we get this low humidity air? Well, it turns out that the air very close to the ice is at the ice temperature, which is radiatively cooled down to -60, -70, and that is lower in temperature than the ambient air near the telescope. Telescope is typically going to be on a tower, maybe 10, maybe 20 meters high, where the air temperature is significantly higher. So the content of water vapor there is greater. So that's a natural source of low humidity air that we can bring up from the ground, from the ice level, and use to reduce the humidity near our telescope. Okay, here's a plot of just some random shot glasses that I found on the web showing the transmission or opacity out near mid-infrared. And you can see that some of these are pretty good. They're, this blue one here, for example, is 70% transmissive in the mid-infrared and quite good throughout the infrared. However, it's not so good in the optical. You have to be, if you're interested in optical, you'll have to look at this very carefully down in this region here. Now, there have been some recent very interesting papers showing how ice forms on surfaces. This is one here, which I'd recommend having a look at if you are interested in this subject. And there's one of the key factors in what happens to water molecules as they start to accumulate is the contact angle between the water and the glass, or whatever the surface is. And here's water inside a test tube and measuring cylinder, and the contact angle is this angle here. And in this case here, it's a hydrophilic substance, which means it attracts water, so it drags water up the glass. And you'll be familiar with mercury, which is quite strongly hydrophobic, where you get a contact angle like that. And this diagram from the previous paper shows the differences in ice formation depending on whether you have a hydrophobic or hydrophilic surface. So this one is hydrophobic, and you get what's called OSG surface growth. That stands for off-surface growth. This one is hydrophilic, and you get along surface growth. So you can see that water molecules have started to accumulate here, and as they've grown, they've tried their best to stay away from the surface. So the ice crystal forms away from the surface. Whereas if you have a hydrophilic, where the water is actually attracted very strongly to the surface, you tend to get growth along the surface. One interesting consequence is that in the hydrophobic case, you can blow these ice crystals off with a jet of air, whereas hydrophilic, which unfortunately is most telescope optics, a jet of air won't do you any good at all. Interestingly, there's a region around the formation of the crystal where there is not much water. And I suspect what's happening is the water molecules which have gone to the surface are able to jump around thermally and find their way to the electric fields generated by the water at the edges of the crystal. So the molecules aren't just stationary on the surface, they can move. Another interesting paper is this one, which uses atomic force microscopy to actually image the water molecules on the surface of metal, which could be relevant to a mirror. And here are some examples of their amazing images. These individual little blobs here are actually water molecules. I think, in fact, looks like you can see the hydrogen and oxygen atoms. So that's quite interesting. Okay, let's have a look at what to do with icing. And we'll start by looking at internal icing with a telescope optical system. So let me draw a very simple telescope. It's a closed tube. We have some sort of a window at this end, glass presumably. At this end we have a mirror and various other optics inside, which I won't bother drawing. So starlight is coming down here. There's a photon. Inside the telescope we have air. I mean, ideally, if you could put a vacuum in there, the problem would be solved, but that requires a very strong telescope tube and optics in order to resist atmospheric pressure, which may be possible. And I encourage you to look at the ice drake presentation at this meeting, which discusses exactly that idea, having a vacuum to remove the possibility of internal icing. So, but let's just assume we have air. How do we get rid of icing inside the telescope? Well, one option is to put a cold finger inside the telescope. If you can cool down something significantly lower than the air temperature, all of the water molecules can condense onto that. Another thing to do is to put a desiccant in there. And the desiccant is something which absorbs water vapor. And you have to choose that very carefully. You can't just use standard desiccants, commercial desiccants. You need to use something very aggressive because of the very low water vapor pressure. And from my research, calcium hydride looks like the best option. It's extremely attractive to water molecules, and that is worth investigating. If your telescope isn't particularly strong, you need to have a two-way valve in order to equilibrate atmospheric temperature, because the atmospheric pressure changes with time in Antarctica significantly, as it does everywhere, and that can introduce quite substantial forces on the window and the telescope structure. So if you use a two-way valve, which is able to open up if the pressure differential is ever more than a certain amount, air can flow backwards and forwards, and that allows you to prevent explosion of the telescope. You need hysteresis on this, so the valve is only open if there's a pressure differential. And I'll show you a paper which allows you to calculate that in a second. Okay, so how do you detect and remove ice? Well, you can, let's draw a part of an optical telescope. Here's a window. To help, you put a baffle on the front to reduce thermal radiation losses. I think a good idea is to have a heat lamp inside your telescope, which can illuminate evenly the window. This is outside. You need some sort of a detector emitter system. You can use an LED and a receiver with a synchronous detector system so it's immune from DC offsets. And then we need to blow low humidity air over the outside of that window. And I think if we do all of those things, we will succeed. The heat lamp only has to be on intermittently, can be between readouts of your detector, for example, and that should be sufficient to remove the ice. Finally, there's an interesting paper which we wrote many years ago, which showed the calculation of how much air a bidirectional valve would cause to be accumulated inside a telescope, which was otherwise sealed, based on air pressure data from the South Pole. So it's quite an easy calculation to do. And from this, it allows you to calculate the amount of desiccant that you need in your detector, in your cryostat or telescope volume. Okay, that's it. Hope you learned something interesting, and do let me know if you have additional ideas. Okay, that's all.